Good morning, good afternoon, good evening, good night, whichever is applicable to you. Welcome to our Chapter 9 virtual lecture. This is something or the chapter on periodic properties, which I believe you have or we have covered most of the concept we'll talk about in Chapter 9, periodic properties of elements. We looked at the beginning of the semester. Periodic table, naming the elements, and writing the chemical symbols. And in chapter 9, we will look at the how elements react based on the group. And without wasting my time, this is the chapter outline. We will look at the nerve signal, what causes the nerve signal in transmission. 9.2 development of the periodic table, electron configuration, how electrons occupy the orbital in section 9, in the 4 electron configuration, electron configuration. Good morning, good afternoon, good evening, good night, whichever is applicable to you. Welcome to chapter 9, our virtual lecture. This is a chapter on the periodic properties of elements. At the beginning of the semester, we looked at the elements on the periodic table, writing the chemical symbols, writing the chemical names, and we have looked at, or we looked at how the periodic table can be broken into metals, metalloids, non-metals, or semi-metal for metalloids. In chapter 9, we will look at the periodic properties of those elements. When we talk about the periodic properties, means periodically there are some recurring chemical reactivity of those elements, physical properties of those elements. In chapter 9, this is what I will cover, section 9.1 all the way to 9.9. However, I will not go all the way in one session. The lecture is split into 3 parts, part A, part B, and part C. We'll start with part A, and in part A, we will cover section 9.1, 9.2, and 9.3 before we shift gears to part B and part C. In part A, let's look at 9.1. In 9.1, it's about the other talks about the nerve signal, the movement of ions across the membrane is responsible for transmission of the nerve signal. And here, these are the ions responsible, sodium and potassium. The transmission has to do with how the ions carry in sodium, carry into the cell, ions out, and potassium ion in. This is the transportation or the movement of these two ions across the cell membrane. You see, the transmission or the movement of these ions is selective in such a way that both ions does not move in the same direction, does not go in and does not come out. But from this illustration here, sodium get into the cell or across the cell membrane, and potassium get out. There is a channel which controls the movement, and you may wonder what is selecting this or why. It has to do with the size of these ions. Let's just think about as this is sodium ion, is relatively small. This is sodium ion compared to potassium ion, Ki positive. The two, they are different in size. This is the subject of chapter 9. There is a pattern where this element, even though potassium and sodium are in the same group, remember group 1 on the periodic table, sodium and potassium, they do not have the same size. As you go down the group, you see this is group 1, the radius or the size of the ions increase. This is the radius, this is the radius, the size keeps on increasing. This is one of the patterns we will talk about later on, but for this section 9.1, you can read in the text, it's about the movement of sodium ion and potassium ion, and there is the channel control of this, how this ion moves, and it has to do with the size. It has to do with the size. That's what we'll be looking at in chapter 9, periodic properties of elements. These are group 1 elements. And without wasting my time, let's look at the section 9.2, all right? Section 9.2, this is the development of the periodic table, how the periodic table has been organized. There are several scientists who actually contributed towards the development of the periodic table. However, Dmitry Mendeleev and Myers, some German scientists, came up to the same conclusion almost the same time. However, Mendeleev is given credit for the modern periodic table because he was able to predict yet undiscovered elements. Lothar Meyer did not propose how to predict future elements. They will never be found, but Mendeleev was able to do that. We'll see that, or you may have seen that he predicted 2 elements which they were not existing during his time, and Mike later the physical properties and chemical properties of those elements were exactly what Mendeleev had predicted. A point to mention here is he was organizing the table based on the oxide, masses of oxide. He was reacting an element with the oxygen and then weighing it, all right? I'm saying that this is way, it didn't work all the time, because if you look at the atomic mass of argon and atomic mass of potassium, they do not follow the pattern as in number 18, number 19. So they should weigh less compared to that, but it's the opposite. You see some anomalies, even cobalt and nickel, they don't weigh the same way, even though it was actually using atomic masses of element to organize the periodic table. What you see under here is just the timeline, how the elements were discovered. During ancient time, there were only 9 elements, and there was no need to trying to organize them. But as more elements were discovered, there was a need to organize the periodic table the way it is. If you look at here, around mid 17th century, a lot of elements were discovered, around 42 of them, and more are being discovered, and there was a need to organize the periodic table. You should make your own notes on the scientists who contributed towards the development of the periodic table. One of them here I've just mentioned, Dmitry, is credited for organizing the periodic table according to atomic masses. You see, this is according to increase in atomic masses. On the right corner is his picture. I guess this is his graduation gown. He was organizing the table according to masses of oxide and putting element recurring periodically, which we call periodic law. You should be able to state that. You may see this in the exam, you may see this in the quiz. Periodic law states that when elements are arranged according to increase in masses, certain elements keeps on repeating. That's what he was using. And I have underlined here that masses, but modern periodic table is based on increase in atomic numbers, not according to their masses. So this is what he was doing in organizing the periodic table. Now, Henry Moseley, who was an English physicist from Britain, modified Mendeleev's periodic table by organizing the table according to increase in atomic number, hydrogen number one, helium number two. And what he did was he performed an experiment where he was bombarding the nucleus of the elements, and there was increase in the nuclear charge. The reason why he did that is because Mendeleev's periodic table, there was some questions Mendeleev could not answer. For example, let me show you on the periodic table why Moseley had to modify Mendeleev's periodic table. Here is periodic table. This one doesn't show atomic masses. I want the one which shows atomic masses. Probably this one. Let's see if it's going to enlarge. If it doesn't enlarge, you will see how the periodic table look like. Right. Okay, the periodic table of elements. I can pull one with the numbers. Let's see this. This one doesn't have the numbers. I want the one with. Yes, this might work. So if we look at, let's say, for example, cobalt and nickel, atomic mass of cobalt is 55.93, whereas for nickel, it is 55.63. So this one way more than couple number 27. And if we were to follow Mendeleev's proposal, nickel should be here, cobalt should be here. This is not the only, or these are not the only elements which doesn't follow increase in atomic masses. Like I said, let's see, argon, for example, is number 18. It weighs 39.95, but potassium is 39.10. If you look at that, number 18 weighs more than number 19. So 19 is lighter than number 18. And that is why mostly now, let's go back to our slide. Let's see. If we go back to our slide, you'll see why Moseley had to develop a concept of atomic numbers. And this experiment was just bombarding the nucleus, and the increase in the nuclear charge is because of the number of protons in the nucleus. Remember, hydrogen has one proton, helium has two protons, lithium has three protons, and that is where we are right now. The modern periodic table is organized according to increase in atomic number, which was proposed by Henry Moseley. This is how you should define periodic periodicity, it is, or periodicity or periodic law, in other words, states that when elements are arranged according to increase in atomic number, certain physical properties and chemical properties keeps on repeating. All right. If we organize the periodic table according to increase in atomic number, certain physical properties and chemical properties keeps on recurring. In this chapter, these are the some of the properties we will discuss. The sizes of the atoms or ions we saw in section 9.1. The size of sodium ion is smaller than the size of potassium ion. We will also talk about the ionization energy, which is the minimum energy required to remove an electron from an atom in gaseous state. Electron affinity, the amount of energy given off when an electron is added into a neutral atom in gaseous state. Some selected groups also will look at their properties and their trend. That is what we'll be looking at in section or in chapter 9. You can make your own notes on this. Mine will just be the skeleton. Here is an example of a question you expect to see probably in the quiz, in the exam. Who is credited for developing the concept of atomic numbers? The correct answer is A, Henry Moseley. Henry Moseley is credited for organizing the periodic table according to increase in the nuclear charge or atomic number. There are other scientists which I want you to also read in section 9.2, development of the periodic table. Lord Tamai, as I say, they were working the same time as Mendeleev. They came to the same conclusion as Mendeleev, right? But he didn't propose yet undiscovered element. Dmitri is credited for the modern periodic table. These two are the guys. Faraday, we never talked about this. Ernest Rutherford is credited for the nuclear model of an atom. You need to know all these names because you may be given things that, oh, I've heard about this and you don't know. So there is other scientists which I want you to remember what they contributed. There is the Newland. Right, you can to know Newland. You need to know their contribution as well. Newland, the law of triads. This first name is John. He proposed the law of octave. His proposal only worked for first 20 elements or so, and the octave for 8. He proposed that when elements are arranged, the 8th element keeps on recurring. There is the John is credited for the law of triads. He was organizing the elements according to groups of 3. John Deponere is credited for the organizing the table according to the 3 elements. They react the same way, 3 of them. They react the same way. He didn't make a breakthrough. So these two, they didn't make any significant contribution as such, but you need to know their contribution towards the development of the periodic table apart from Henry Moseley atomic number, and Dmitri is considered as the father of the modern periodic table. This is now reason why Mendeleev is credited for the modern periodic table. He was able to predict yet undiscovered element during his time. If you look at the periodic properties of calcium, all right, this is what he proposed. Calcium equal Aka. Aluminum, that means compete for the aluminum. If you look at the position on the periodic table, this is what he proposed that it's going to be about 68 atomic mass unit. Low, he didn't specify the actual uh, melting point, but this is significantly low compared to melting point of other elements on the periodic table. Look at the density. He was right on money. Look at the chemical formula for the oxide. Look at the chemical formula for the chloride. This is the actual, this is what he proposed. Even germanium is the same thing. This is the reason why Mendeleev is considered as the father of the modern periodic table. Meyer did not propose yet undiscovered element, even though they came to the same conclusion as Mendeleev, same conclusion in Mendeleev. Now, Mendeleev's periodic law allows us to predict what, but doesn't explain why the pattern looked the way it is. What we learned in chapter 8, quantum mechanical model of an atom. Here now, the quantum mechanics explain why the periodic trend or periodic properties keeps repeating, keeps recurring the way it is on the periodic table. Knowing why allow us to predict what, So we're going to be using what we learned in chapter 8, quantum mechanical model, those to explain the recurring physical and chemical properties of elements. Well, let's shift gears. Before I dive into section 9 or section 9.3, please make your own notes on section 9.2, development on the periodic table. You should know those key figures, key scientists who tag them to their contribution towards the development of the periodic table. Well, 9.3 electron configuration. I just define electron configuration loosely. Electron configuration. This is electrons are arranged in an atom. There is a pattern in which electrons occupy the energy level we talked about in chapter 8, principal energy levels, level 1, level 2. Remember, I say that the energy of an electron is quantized based on the shell, based on the energy level it occupies. Now, in chapter 9, we'll see how those shells are occupied by electron and the exercise by which you arrange those electrons in an atom is called electron configuration. In order to master electron configuration, you need to learn this principle. I hope I got the right spelling. Let me just make sure that we are on the right page so that I don't give you wrong information. Yes, there is A here, and then there is U here. There is no A here, so that is how that is A U F like that principle. This will help you in mastering electron configuration. Uh, they are three methods of electron configuration. Three methods of electron configuration, and all of them, they are anchored, or if you master this principle, it will be very easy for you to interpret the three methods of writing electron configuration. But first, let's see how this principle works. All right. Remember, from the quantum mechanical theory, electron exist in orbits, and in orbitals, not orbit, in orbitals. Remember orbitals right here, we described this before. Orbital, this is a region of in an atom where there is high probability of finding an electron, or finding an electron. That is the definition of an orbital. We defined that earlier on. You should also know this is where the electron will reside in chapter 9. The description of orbital occupied by electron is called electron configuration. This is hydrogen, this is an orbital, s orbital, there's p orbital, and this is the principal energy level. This means number of electrons. According to this principle, electrons occupy the lower energy level shell before occupying the higher energy level shell, and so forth. Just like if there is like a skyscraper with 110 floors, you maybe occupy second floor or ground floor. There is no way you can go to 110 if there is no an escalator. So electrons occupy shells or orbitals with low energy before filling in orbitals with higher energy. According to this principle, this is what you need to learn. And I know you may have learned in Introduction to Chemistry 1S2, 2S2, 2P6, 3S2, 3P6, 3B10. Let me just stop here for a minute and explain what is going on here. This is shell number 1, this is shell number 2, this is shell number 3. Now, the superscript, but before we get to the superscript, this is the sub-label. S sub-label, P sub-label, D sub-label. Remember, there is S, E, D, F, all right, G, H. These are sub-labels. Sub-label. And the superscript indicates the maximum number of electrons we can go in each sub-label. For example, S can take only a maximum of 2. P sub-label take a maximum of 6. D sub-label take a maximum of 10. So remember that. And then we continue with 4S2. Now you know the pattern. 4P6, 4E10, 4, 14. It's the maximum number of electrons increased by to 2, no, pi 4. 2 plus 4 is 6, 4 plus 6 is 10, and so forth. 10 plus 4 is 14. So if I go to the 5th energy level, This is the fifth energy level, 5s2, 5d6, 5d10, 5f14. Is continuous continue. And then 6s2, 6b6, 6b10, 6f14, 7s2, 7b6, 7b10, 7f14. In case you're wondering what the dots means, if you look at shell number one, there are one sub-level. In shell number two, two sub-level. It is SMP, three sub-level. So every time you increase shell, the number of sub-levels equal to the shell number. We learned this before. So in shell number four, we should have four sub-level. 1, 2, 3, 4. In shell number five, we should have 1, 2, 3, 4. And that is what is meant by this dot right here. Shell number six, you should have 6. 1, 2, 3, 4, 5, 6. Shell number seven, you should have 7, but we don't need that so long as we have mastered how to write the electron configuration. Now, this you need to note that electrons sublevels according to increase in energy. According to increase in energy. How will you know that electron will occupy what in this sublevel? I want you to master how you properly align sublevel so that the next thing, in order to know how the electron occupies the sublevel according to increase in energies, draw a diagonal. If you look at the pattern, an arrow, and you start with the pattern here, you cross one by itself, one. So one twice, two twice, you see two twice, two sub-levels are an arrow going across. And then for the third one, we will have to join three of them. We'll have to join three of them. So if you look at there is 1, 1, 2, 2, 3, 3. So if we have 4, if you look at 4, 1, 2, 3, 4, you can stop there. You can do that, you can stop there. Now we join the head and the tail. The head and the tail, the head of the arrow, the head of the arrow with the tail there, the head of the arrow with the tail there. Now, if I write, let's say start here, and then and I want to end there without lifting my iPad pencil. Without lifting my iPad pencil, I just go zigzag, 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 start here and here. This is the pattern. It will be 1s2, 2s2, 2p6, 3s2. In case you're wondering how that is playing around, is this 1s1, I'm down, 2s2, 2p6, 3s2, 3p6, 4s2. So after 3s2 is 3p6, 4s2, 3d10, 3d10. You see, 4s2 here, you go back to 3d10, 4d6. So it's gonna be this is 10. 4d6, 5s2. After 5s2 is 4d10, 5d6. 4d10, 5d6. 6s2, 4f14, so 6, 2, 4, 4f14. 5d10, 6d6, 5d10, 6d6, and then 7s2. So this is 7s2. 7s2. What I've done here is write the order in which the sublabels are occupied by electron in an atom according to increase in energy. According to increase in energy. Once you start from here, you end up with that, and then you are done with the three fashions of writing electron configuration of an element. Let's start off with the first element on the periodic table, which you should know that our hydrogen, neutral hydrogen has one electron. You don't write two, but you write just hydrogen is 1s1. It has one electron. For helium, 1s2, just two electrons. For lithium, look at this. Lithium, it is not 1s3, but 1s2. We are remaining with 3. No, with 1. So this is, we are remaining with 1. So 1s2, 2s1, because lithium is number 3 on the periodic table. It has 3 electrons. So here is, you have to go sequentially that you have 2, and then there is 1 to make 3. You reconcile the atomic number on the periodic table with the numbers. You should add what the subscript so that you have the actual numbers. If we look at what else do we want to try? Let's say nitrogen. Nitrogen is number on the periodic table. Nitrogen is number 5. All right. If you look on the periodic table, nitrogen is number 6, number 7. So it's number 7. So if this is number 7, it has 7 electrons. This is 1s2, 2s2. How many remaining to make the 7? It's 3. So it's going to be 2p3, 2p3. You do this reconciling the atomic number with the sum of the exponent in this sequence or pattern in which the electrons are placed in subshells of an atom, or rather, how subshells are occupied by electrons in an atom according to increase in energy, and those according to increase in energy. So that's how you write the electron configuration for our element. In case you're wondering how comes that we have one of these, it extends beyond that to other elements as well, So we can have sodium, for example, and A, which is number 11, 1s2, 2s2, we have 2s2, we have 4. 2p6 gives us 10, 3s1 gives us 11. So that is how you write electron configuration for any element. You'll be given the periodic table. You'll be given the periodic table, look at the atomic number, and then you write the electron configuration. Please practice the long form. I call that the long form. So this is method one. Yeah. Method one. There are three methods. Before we look at that, let's go back to the fourth quantum number, the ms, which is the spin magnetic quantum number, which describes how the electrons behave in an atom. If two electrons occupy the same orbital, they have the opposite spin. This was demonstrated by the calculation with Schrodinger equation. The spinning here is this is the spinning electrons. Electron spin. If this is an orbital, we call this spin. And it is plus 1/2 minus 1/2. This is the spin right here. This is the spin. They are commutative. You can put on the other side. So that if we have that, the magnetic spin will have impact on how we write the electron configuration. It's a fundamental property for this. We talked in chapter 8, the quantum magnetic, the spin quantum magnetic number, ms, which is what we're going to use in chapter 9 to see how the spin affect the electron, just plus or minus value. Spin must cancel out when they pair. Of course, when you have one plus, half a plus, and the negative 1/2, and the positive 1/2, if you mix together, they cancel each other. They cancel each other. They don't face in the same direction. We're going to talk about that momentarily. So method 2 is orbital filling diagram. So here, then we'll say method 2. It is called orbital filling diagram. You see how hydrogen, if I'm to write helium, they must have opposite spin. So assume this is 1s. For lithium, you may even have dashes. Let's just even forget on these dashes. This is 1s, 1s, 2s. So this is 1, 2. You occupy the first lower fast before you move on. So for lithium, the 1s is completely filled up. And we come to what follows after that, 1 electron. This is for lithium orbital filling diagram. Orbital filling diagram. So this is how you write orbital filling diagram. The direction of the arrow represent the spin. So this is spinning in that direction. This is spinning in this direction. You can use 1/2 or have an arrow or full arrow. Nitrogen is number 7 on the periodic table. We have to write the electron configuration. It's assumed that we have learned about the Hans rule, which we'll talk about later on, and Pauli's exclusion principle. However, the correct answer for this is the I know you are maybe wondering how did we end up here, but just trying to see if you know how to write the electron configuration for nitrogen. The problem with A, you do not pair them up until they are singly occupied for degenerate. When I talk about degenerate, they have same energy level. The correct answer is B here. Fully occupied, the lowest before you start pairing them up. Pairing them up. Learning check ground state electron configuration for Phi is what you need to know. What is the element represented by letter V, as in Victor? On the periodic table, we learned this before, all right, which I know you remember. This is vanadium number 23. So if I was to do the math, you'll have to see which one has electron configuration. When you sum up, and they're in the correct sequence, gives you the total number of electrons. In this case, A is the correct answer. If you still have some answers for this, you can come back. Nevertheless, this is how you arrive at that. Once we know the atomic number, which is 23, we add the superscript numbers. 4 plus 6 is 10 plus 12, 18, 20, 23. 3D3, that's why we have A right there. A. Now, please look at more worked example in the text. Now, which element has a ground state electron configuration? So sometimes you may be given an electron configuration and you're asked to find the or identify the element. Here, the xenon is number 54. Xenon is number 54. So you add 54 plus 6 gives you 60. And the atomic number 60 is D. Number 60 is D. Chromium. That's not the correct answer for this. So the correct answer is D as in David. D as in David. D as in David. There's a principle here. Before we look at orbital filling diagram, we look at the how electrons behave in an orbital, or how electrons occupy the degenerate orbital. Pauli was an American chemist, having known how many electrons goes in each sublevel or sublevel SPD anywhere, regardless of the energy level, the number of orbitals, and the maximum number of electrons. Pauli explained that when degenerate orbitals are occupied, they are simply occupied first before you start pairing them up. In other words, you don't pair the electrons and these they are simply occupied. A, this is wrong because there is a pairing before simply distributing it. One, other orbitals. This was wrong because argon cannot have, or rather, the two electrons cannot spin in the same direction. They must have opposite spin. This one, you do not pair them up until they are simply distributed, until they are simply distributed. So if I look at C, this is correct, right? Pauli's exclusion principle, which one? violates. Yeah, we are looking at it. Violation, which is B. Violation, no parent. The correct answer is B. Wondering for this question, there is no pairing. Remember, Pauli's exclusion principle states that no two electrons can pair them up. Now, there is a Hans rule here, which states also that when degenerate orbitals, they occupy the lowest before you start pairing them up. If you look at all the electron configuration here for lithium all the way to sodium, they are the degenerate orbitals. You don't pair them up until they are singly distributed. What this means, you don't just take highest level, leave some empty shells to maximize the energy they occupy the lowest level. This means for a set of orbitals in the same sub-level, what we mean by same sub-level, like this, they are on the same sub-level, there must be one electron in each orbital before pairing them, degenerate. Lowest energy level is reached when the number of electrons with the same spin is maximized. This describes Hans rule. We just look at that. So you should be able to state Hans rule, like you are almost. You should be able to state Pauli's exclusion principle. Pauli's exclusion principle is about pairing them up, like when they are paired, they should have opposite spin. Hans rule states that they are singly distributed first before you start pairing them up. You need to remember that. So which orbital diagram violates Hans rule? The correct answer is D. Why D is, according to Hans rule, degenerate orbitals are singly occupied before you start there. Why do you have to pair this, yet they are still empty orbital? This is violation of Pauli's exclusion, not Hans rule. No violation here. Hans rule because you didn't pair them up. This has to be filled before you start filling the rest. Read on Hans rule as well so that at least you know what Hans rule and Pauli's exclusion principle is all about when you write the electron configuration for element using orbital filling diagram. Orbital filling diagram. This is just a review of the quantum numbers, in particular focusing on the spin and the orbital, how the electrons behave in an orbital using helium. Helium has two electrons, and these two electrons, they have the three quantum numbers the same except the magnetic spin quantum number. They cancel out when they are paired, but if they are not, then they will not cancel out. Sub-levels, you may have been wondering why there was a splitting. Let's go back to power, the whiteboard. This is what I want to highlight. If you look at the three D4S or here, 4D5E or here, five B comes after 4D. The overlap here has to do with the splitting in multi-electron, multi-electron orbital. So how are we going to use that to fill up I will get in details into penetration, but here is what I want us to look at. Let's say for quantum numbers, electron configuration. So here is the third. We have looked at the first one. This is method one, the long one. The method two, orbital filling diagram, and then method three here. I'll call this short. It is abbreviated. Before we look at this, method three for writing electron configuration shorthand. In method three, uses group 8 elements to account for core electrons. Core electrons are electrons in the innermost shells. This is what we call valence electron in the outermost shell. We're going to talk about in section 9.4. So if you are asked to write the electron configuration for, let's say, magnesium is number 12. You will write as 1s2, 2s2, 2p6, which is 10, and then 3s2, which is 12, or 1, 1, 1, 2, 3, 1. So that this is 1s, and then this is 3s. Let's fill with the electron. This is going to be 1, 2. You fill the sub-level first. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is the orbital filling diagram showing you method one, method two orbital filling diagram. And then last, the method three is using group 8 element. We use group 8. To indicate for electron. That is for magnesium. I need to pull the periodic table from here. You go look at the element in question, go pack one row, go all the way to the end. That will be number 8, the element in number 8. For example, magnesium is in row 3, go one step, then go all the way to see which element you're pointing. So we're going to use in parentheses neon. This indicates the inner electrons. So this is going to be 10. Now, up to here, this is neon. So you write 3s2, 3s2. So that is how you write 3s2. Shorthand electron configuration for magnesium. For krypton, it's just gonna be like that. There's nothing outside. For neon, it's just gonna have that. For xenon in parentheses. But if there is something, you need to learn the other one first so that you know what success you have with it. Let's say for chlorine, you see chlorine, B17 would be 1s2, 2s2, 2p6, 3s2, which is strong. We need 5 more, so it's gonna be 3p5. So if I use the shorthand, it's gonna be neon. This is neon, and up to here, we have neon, which is 3s2, 3p5. This is the shorthand electron configuration for neon, electron configuration for neon. Also learn the 3 methods. You should be well-rounded for that. Let's move on to 9.4. This is on valence electrons, electron configuration, valence electron, and the periodic table. Let's define first of all valence shell. Valence shell is the outer most shell. So that's how you divide that, or with the highest n value. So if you write electron configuration of elements, you will see that the ISN is, we call that valence shell. For example, here, this is the valence shell here, valence shell. And valence electrons here, the electrons in the highest principal energy level are called valence. So here we have, and if you look at this, it's not the P sub level. Chlorine, we have 5 here. This is P5. Don't count the sub level P and say it's the outer. It's the sum. So here is 2 plus 5 equals to 7. Valence electron for chlorine. You don't need to write electron configuration to determine the valence electrons in an atom. For main group element, notice, note, for main, right, main group elements, valence electrons equals to group number. For example, group 1, they will have 1 valence electron. Group 2, they will have 2 valence electron. NP is helium. Why is exceptional? What is the exception? Exception is this. If we say all for main group element, that is the A, you know what main groups are, valence electron equal to the group number, how comes that helium has 2 electrons? How will it end up with 8? Helium is in group 8 and it's an exception where we cannot use the group number to determine the number of valence electrons. So what actually is responsible for reactivity of elements, or rather atoms of elements, is the outermost electrons, which is available for forming the chemical bond, for reaction. It is important for both chemical and physical properties, the number of valence electrons. So far, you should know what valence electrons are, how to use the group number. Let me just go back to periodic table. This is group 1, they have 1 valence electron. Group 2, they have 2 valence electrons. Group 3A, group 4A, group 5A, group 6A, group 7A, except for helium here. This is what I say, except. It's in group 8. It has only 2 electrons. The rest will have 8 valence electrons. Will have 8 valence electrons. We use the group number. So electron configuration, if you look at the outermost highest n value for mu, they have 1 valence electrons, 2 valence electrons. These are just group, 6 plus 2 is 8, they are in group 8. 5 plus 2, they are in group 7A, and so forth. You can learn more. I know we learned this before. Group number, and here is the outermost, the highest n value for group 5. We are missing. Don't think that in group 5 this is the electron configuration. That's not the electron configuration for group 5, but we are looking at the outermost shell. Here are some bullet points you need to take home moving forward. The main group, when we say main group, those are the groups on the periodic table, which are numbered using a letter and a number, and the A, 1A. Let me just say here, main group, or representative elements. They have the same thing. These are the 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. These are main group. When we say main group, given the periodic table, the first 2 columns and the last 6 columns on the periodic table, we use the group number to determine the number of valence electrons. Now, the length of each block is the maximum number of electrons the sublevel can hold. The length, what does that mean? If you look at it here, number on the periodic table, the length here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So D sublevel will take 2. This is S sublevel. P sublevel takes a maximum of 6. This is the length of a block. Remember the S block, P block, D block, the F block right here, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. They may have increase, should be 14 for this, because lanthanide shouldn't be here. Lanthanide should be here in periodic table. Let me just confirm. From the text, I got that from the internet. You may not really see here, but if you refer to our text, lanthanide should be in here so that we are 14 in length. use the periodic table archive view, it should have 14 for that. That's what is bullet point number 3 here means. The periodic number corresponds to the principal. The period number corresponds to the principal. What does that mean? This is period 1, row 2, row 3, row 4. This is the fourth principal, the fifth, and so forth. So principal period corresponds to the principal. Principal is energy level. So if I say 5s2, let's see here, 5s2 or 4s1, just to give you, this stands for energy level 4, energy level 5, energy level 7, energy level 6. Principal energy level. The number indicates the energy level. This is the sub-level, let's see, learning check. Which group in the periodic table contain the element with the valence electron? This is just what we looked at, the valence electron. All you have to do is add the superscript numbers, and you'll end up with the number. This is for group 3A because of 3 plus, 2 plus 1 is 3. If it is group 1, 1s1, this is 1A, 1s2, this is 2A, and then 1s2, 2s1, this is 3A, which is the subject. You don't even see, this is N and N, principal. N here stands for principal. So I can have NS2, NP6, this is 8A. NS2, NP5, this is 7A, and so forth. You need to learn what the valence, we are talking about the valence, highest N value here. We don't know, it can be any number, but what is important is those electrons in SNP for main group as to the valence electron for that element. These are just the blocks of element. I know you, we saw before the outermost electron configuration. It was NS, NP, and S143A. You see this? It can be 2, 2, it can be 3, 3, it can be 4, 4. But when you add the superscript, we are 3A. You can do the same thing here. This is 6A, this is 6, using the blocks of element. So here is the correct periodic table I was trying to count before. Lambda 9 should be here, not here. That one was from the internet. But if you look at here, this is the copyright, this is the book, so it should be 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, yes. Lambda 9 series, they just come out the Lambda 9. So these are the plots of elements, so earlier on, and when we say plots, it depends, plots of elements depends on which last electrons goes in. If the last electrons end in S sublevel, we say that element is an S block. These are S block element. If the last electron in electron configuration goes in P, we say that is a P block element. You see helium is still S, even though it's right. Now D block element, these are F block element. That means the electrons, the last electrons are in the F block element. That's how these blocks of elements are organized. Now, without writing electron configuration, determine the number of valence electrons for nitrogen. Nitrogen is in group 5, so it's 5. So given the periodic tables, you should be able to write the electron configuration for any other element or predict the number of valence electrons without writing. Given the periodic table, you should be able to predict the number of valence electrons for that neutral atom. So for example, you see. How to write, using the periodic table, you can use periodic table, right? Locate the element, the position of an element on the periodic table tell you how many electrons. Hydrogen is number one, it has one valence, it has one electron. Helium on the periodic table, 2 electrons. Lithium, sodium, 11 electrons. Chlorine, 15 electrons. Magnesium, 12 electrons. Fluorine, 9 electrons. Carbon, and so forth. Please, just use the periodic table. The atomic number equals to the number of electrons. If you are to use the shorthand, look at the preceding element, all right? Look at the preceding element. And then you determine, when writing the symbol for that in brackets. So if you're using the shorthand, use the bracket. Determine the outer electron configuration. Yes, so if there is something else outside, you need to remember that. What that means is, if let's say you are writing for magnesium, neon is 10, 3s2. This is magnesium Mg, and that is what's all about item number 4. You will not know how many electrons are accounted for by the core electron. You need to know the LAN or LAN, the long form of electron configuration for you to do that. You can use the periodic table to write the electron configuration, in the sense that going across, this is P1, P2, P3, P4, P5. So the outermost sublevel here is P5. This is 3s1, 3s2, 4s1, 4s2. And then when you come to 3D, this is 3D, 4D, 5D, 6D. This is D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. You can use the periodic table. 1s2, 2s2, 2p6, 3s2, 3p6, and so forth. And then you write the electron configuration without writing the other one. We learned the long form. You need to understand that there's some irregular electron configuration on the periodic table, which doesn't follow the pattern. Within the first 30 elements, chromium, let's see, if someone asks you to write the electron configuration for chromium like that, Cr, which is number, this is number 24, I believe, number 24. We look at the periodic table. Chromium is number 24 here. This is chromium number 24. If someone asks you to write the electron configuration, I know some of you will say, look, if we were to do the way we did before, 1s2, 2s2, 2p6, look, 2p6, 3s2, 4s2, that's 20, 3d5. No, 20 to make 24. 20 up to here we have, look, up to here we have 20 electrons. We have 20 electrons to this. So how many do we need here to make 24? We need to have 4. Somebody might think that this is how it should look like. No, this is wrong. For chromium, it's going to be 1s2, 2s2, 2p6, 3s2, 4s1, and 3d10. You may ask how and why. It turns out that the atom is stable when the D is half, or this is not completely full, but when electrons are half filled, this is 5. I took one from the S2, you see this, took one to make the D sublabel a half filled. Remember, D can take up to 10, a maximum of 10 electrons. 5 is halfway. Therefore, instead of just being 4 and 2, when it is halfway, this is more stable than this. This is stable. Say that this is unstable. This is unstable. We say that it's unstable. So if I'm unstable, we go with this. It is abnormal. So if I'm to write the shorthand for that, it's going to be argon. It is 18 electrons here. 18 electrons, and then 4s1, 3d5. This is the correct electron configuration for chromium. Likewise, if you look at copper, number 29 on the periodic table. This is copper right here. It's number 29. So if you are to write the electron configuration for that, this is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d20 to make 29, you say 3d9. But this is wrong. This is wrong. The way it should look like is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, no, 4s1, and 3d, let me highlight this, 3d10. I'll just write the way I write it and promote one electron to make the 3d sub-level fully occupied by electron. This right here is unstable, and this is stable right here. And this is the correct, this is wrong the way you do. So I've shown you two within the first 30 element of the periodic table, chromium and copper, number 24 and number 29, they have an irregular electron configuration, there are other, apart from this, there are other elements with irregular, all right, electron configuration. The first two, based on the first 30 element on the periodic table, I've given you that. These are the element on the periodic table with abnormal electron configuration. You'll have expected for chromium, but this is the truth. Look at the copper you have there. If I look at most of this is D4. You make it 5. B9, you make it 4. You see 5 and 4, make it 5. Except for this, all right? Here we will make it 10 to be stable. Remember, we had to make here 10 to be stable. Here is 7 is almost 10 for rubidium. These are just few. You don't need to worry that might learn, but you have to be careful. The first on the periodic table is given that you should know that they are abnormal. For example, here what is the crown? Okay, what is the correct crown state electron configuration for chromium? You need to recall the chemical name, chemical symbol of element, because if you don't know the position, all right, chromium is number 24. The correct answer is B. You need to know the chemical symbol. My periodic table in the exam will have only symbols, not the names. And if you don't know, you'll just get stuck and you won't be able to move forward. This marks the end of part A. We will come back again in part B. Thank you.